Alright, this is the motion section. I've condensed this all into one thing so I don't have to go through 2 pages for this first question. But there's Mr. Herman throws the ball up and it comes down again. And then there's these 6 graphs and you've got to choose these graphs for each question. So the ball goes up, the ball comes down. Which best describes the displacement of the ball versus time for the time the ball is in the air? So which of these graphs shows how the displacement, so we're going to have how x changes. I'm going to have time and we're going to have x up here. So he starts off, the ball's close to his hand, yeah, we know that. Then the ball gets further from his hand, so at one stage the ball's quite displaced quite a while, and then it falls back down and it's in his hand, so the displacement at the end is 0 again. So which graph goes through these 3 points? A, B, C, D, or E, or F? So it must be A. Okay, a graph of displacement time looks like that. So that's the first one. Which shows the velocity of the ball versus time for the time the ball's in the air. So time and velocity. Well, when it leaves his hand, it's going really fast in the upwards direction. So it's got a big velocity as it leaves his hand. As it gets to the top, it momentarily stops, so the velocity goes down to 0. And then as it comes down again, its velocity increases, but it's going in the negative direction. So up is positive, and down is negative. So the velocity ends up being negative on the way down. So this velocity graph looks like this, which is, according to these graphs, graph D. Now the other way you could have got that is by taking this one and going, what's the gradient? Okay, the gradient starts off positive, quite big, it's here. The gradient along the top is 0, here, and then the gradient here is negative. Okay, and that's why this part's negative. Which describes the acceleration of the ball versus time for the time the ball is in the air? Acceleration time. Now I'm going to draw this down here because some of these graphs you can see are going below 0. 2 ways you can do this. Again, you can go and say what's the gradient of this graph, because the gradient of the velocity time graph is acceleration. Well, the gradient of this graph is the same all the way and it's negative. So it looks like that. The other way you could look at it is by saying, well, what's causing the acceleration of the ball? It's gravity. Gravity is in the downwards direction, which is what we're calling negative, and it doesn't change. It's always the same. Which graph looks like that? Is it F? It's B. Alright, the gravitational potential energy of the ball. So the gravitational potential energy equals mgh. The h is the displacement in that direction. Okay, so when h equals 0, the height equals 0, it's because its displacement equals 0. So this graph, because there's an h, and the h is the displacement, it's going to be the same as displacement graph. I.e., the gravitational potential energy is going to look like that. And that graph was displacement graph of A. Right, last one. Which graph best describes the total energy of the ball versus time? So as sum of, well, maybe I won't use that so much, total energy. It starts off down here, the ball has a lot of kinetic energy. Up the top, the ball has a lot of gravitational potential energy, and that bit turns back into kinetic energy. But overall, the total energy anywhere is the same. Total energy anywhere is the same. And that gives our graph of F. Total energy, well, this graph doesn't change.